Okay. Okay. Give me one more second and we'll just get oh no, give them one. Coming. Okay. Oh, yes. No, direct chat person, yes. I mean, no problem. I mean, me too, apparently. Okay. I think I'll just let's, of course, if there's any questions about the material, feel free at any moment. But I'm actually just just going to go back to where we were yesterday, Monday. Um, the inclined plane, the lab. And also stop me in I'm assuming you have I believe you told me you're doing part two of Lab 5 this week. I forget which day you guys have lab actually. Maybe you could remind me of that, but in the chat if you wish, if you can. You finished part two yesterday. Okay, thank you. Yesterday was Tuesday. You have lab on Tuesdays. That's interesting. I think I misremembered that. Okay. So you finished part two yesterday. So now okay, so I'm gonna. That's good to know. And so I assume the report. Well, maybe tell me when is the formal report due? Oh, you have lab on Tuesdays. Yeah, I don't know why I didn't realize that or I forgot that. Part next week is due. Okay, thank you, Kyle. Thank you, all of you. Okay, so hopefully everything I'm going to say today is directly applicable and helpful to your formal lab report, to your understanding of what's going on. Also, just so that you know, like usually a lot about the final exam is based on this problem. Like there's a lot going on or in this situation. So I'm not, so everything I'm talking about right now is both to help you actually understand and do the work in the lab or get a good grade or whatever. And it's the material, you know, that helps us close down the semester. I mean, but um, that's my way of saying. I guess that's my way of saying. Even if we get into the details of this, they're details that represent larger concepts. So that's further my way of saying I'm going to start rolling again in a second, picking up where I was yesterday. But since you've now all done the lab, both parts. And since it's now up to you to write it up or understand it, I really welcome. I'm going to even try to put in extra effort today to like stop and invite questions or comments or whatever. Like, really, this would be a very good day for any or all of you to share where whatever difficulties or confusions or the insights you have about the situation itself as it pertains to Newton's second law, free body diagrams, friction, angles, like, because that's the point, as you may have noticed in the lab, like the lab is sort of combining all of those concepts together in one somewhat surprising problem. So please stop me at any moment with either ways you want me to go back or ways you want me to leap forward to something that it doesn't, that you're worried that I'm not going to say. Okay. This is meant to be very directly related to whatever it is that you're thinking about in the class right now. So, so where I think I'm going to back up like a couple of minutes from where I was Monday. Like, if this is a situation, right? If that is the situation, if we're talking about a moment, an arbitrary point in time where the mass is on its way up that plane, then I think the pure free body diagram looks like what I just drew. That's at a moment when the mass is on its way up the plane. In fact, just to get to the chase, at an arbitrary moment when the mass is on its way down the plane, I think the free body diagram looks like this. Right? Um, oh, yeah, I think right there is why there's a difference between what's going on the way up versus what's going on the way down. And that's the only reason there's a difference. Um, I think I sort of skipped it. When you're doing the lab and stuff, you flick the marble and send it on its sort of automatic round trip up and then down. And I believe in the lab, you're supposed to make predictions first of what you think is going to happen. I mean, the whole issue of the whole lab is ultimately how do the times up versus down compare to each other, right? Like that's the whole issue. And I'll say this, that if I, for what it's worth, and we don't want to forget, even if you know the answer now, which I assume you do, but if I were making this prediction, if I hadn't been thinking about formal physics at all and just thinking about life and intuition and daily experience, I would be very likely to predict that if I flicked a marble up uh, an everyday normal inclined plane that was realistic and then let the marble come back down, I would probably predict that it would take longer to go up than to come down. Like, I think that would be a very natural, reasonable. I don't know I think that would be a natural, reasonable prediction that something would take longer to go up than to come down. I mean, just intuitively, if nothing, and I'm not saying it's right, but I mean, that certainly would be my prediction that things have a harder time going against gravity or going up than they do coming down, right? That would be my sort of like outside of physics prediction. Now, then I'll even say if I had taken a little bit of physics, or if I were in high school or whatever, or if I had gotten used to some of the surprises of physics or this or that, then perhaps if someone asked me this question, I might say something. And again, I'm just talking about like spitballing my intuitive prediction of the situation. Then, if I were a little bit used to physics, I might say something like, well, first of all, there's always some kind of thing in physics that I didn't, consider initially. And then second of all, I know from experience in physics that if I throw something up and it comes back down, I am used to believe, like in the air, I'm used to hearing and believing that the up trip and the down trip should be equal because the acceleration due to gravity in free fall is a constant. So whether you're going up losing speed or you're coming down gaining speed, you do it at the same rate. So I might have predicted, well, physics is always a little bit tricky. I think it's actually going to take the same amount of time going up and coming down. Further, and I'm not saying that's right. if I even knew even a bit more, if I knew that somehow accelerations and velocities or that accelerations had to do with forces and things like that, I might even go to the point of saying, well, the forces are like the same on the way up and on the way down. Like there's gravity is doing something, maybe friction is involved, but whatever friction is or however friction works, uh, it does the same thing on the way up as on the surface is the same amount of roughness on the way up as on the way down. So, okay, I'm over talking this, but I might have then had good reason or somewhat of like knowledge to say, I guess maybe the up trip and the down trip are going to be the same amount of time. Now, it turns out, as you know, because you've already done the lab, that, and if you did it, if you got good data, and if you made your angle pretty small, etc., um, you find that neither of those is the case, right? You find that I believe you find, and this is where you should like stop me or weigh in. Maybe I should even take a class survey and find out exactly who found out what. But to cut to the chase, like I think that what you find out in the lab is that it takes less time to go up than it does to come down. In fact, that's why the lab is called slow down. Ha ha ha. But right, it's like slower on the way down. It takes more time on the way down than on the way up. In fact, could anybody confirm or deny in the chat? Like that is what you found for the most part. Yes? Yup. Okay. I see a yup. Okay. All right. And I don't want to confuse you or more than okay, great, great. Yep, yes, yes, great, great. Okay, awesome. So that's the point. Now I'm not trying to unwind that conclusion or confuse it, but I am trying to say, and this is always true in physics, like that's the conclusion and that's like the right answer. But A, if you ever didn't expect that, if that's not what you thought was going to happen, or B, more to the point, if that did happen and you were kind of like, wait, huh? I think we did something wrong, or like, wait, what? Then you're on the correct page. If literally that, and so what we're here to do, what when I go back to the board in a minute, what I'm here to do is unpack exactly why that did happen and why it actually makes sense and like is predictable once we think about it. But I will tell you, and again, I think this is kind of like a secret to physics, is if you just accept that conclusion, if you were never confused at all or surprised at all, and you're just like, yeah, 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 it takes more time to, to come down than to go up. Yeah, 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 obviously, obviously. Okay, formula, formula, formula. If you just treat it that way and never even sort of admit to yourself that there's something funny about that or surprising, or you never engage in why would I have not thought that, and but why do I think that now? Then I really think you are missing something. I mean, not you, I'm not criticizing anybody, but the point of this lab is missed if you just memorize this is what happens. And if I ever thought anything otherwise, I was just an idiot and like I'll ignore that. Like, no, I would think like this lab is meant to be a surprise, and then the goal, not like surprise, but like a surprise, a counter expectational result. And like the goal, the ultimate conceptual goal of the lab is to make sense out of why, even though it seems counter to first instinct, it actually is totally consistent with the laws of nature. Okay, so it all comes down to so again, stop me if anything, if I'm on the wrong. So you're in the right place if you're kind of like, yeah, I kind of get it, but I kind of don't. Like, that's what I'm here for. That's what we're here for. And you're in the wrong place if you're like, duh, duh, duh. I mean, some of you might be, but anyway. So it all comes down to the free body diagrams. It all comes down to these free body diagrams. The fact that the forces that are acting when the ball is going up are identical to the well, they are the same forces as the forces that act when the ball is on its way down. It's normal force, gravitational force, and friction force. And all the magnitudes of those forces are the same in both trips. The difference is that from the up to the down trip, the friction flips direction, and friction's the only force that flips direction. It's the key to the whole thing, right? Now, we see that it's the key once we break the forces into components, which is where I was leaving off on Monday, when class ended. we're going to now, change these pure free body diagrams into component free body diagrams, right? And that's what we did Monday. Well, wait, sorry. Right? The first thing we said, whenever you're breaking up any force, whenever you're breaking up any force into components, the way to know which force or forces to break up is to first choose your coordinate system, right? So we choose an x-axis that is lined up with the expected direction of acceleration, right? So we tilted our coordinate system is the right what we said Monday. That's the key to this whole thing. And we always do this in physics. We always can do physics in whatever coordinate system we want. That's Galileo's principle. So strategically, we choose a coordinate system that's lined up with acceleration. So we tilted our head here. So then we're saying if you look at the diagrams, the normal force and the friction force are fine. They are already lined up along axes. It's the mg that is not lined up along an axis. So we're going to split up the mg, right? That's how you always make that decision. Like here's mg. It has to be split up into two components, each of which lies along a coordinate axis. Now, okay, so one has to lie along the x, and one has to lie along the y. Now look at the way I'm doing this. I'm backing up on the conclusion that I made on Monday, but I'm gonna try to explain it a slightly different way this time. First of all, note, and this is where the practice that you did for velocity vectors and stuff like that becomes really important. Notice, first of all, I mean, even though I'm tilting my head, so now I have a right triangle that's on its side, which tends to throw people off at first. Like the hypotenuse is a vertical line now, but that's okay. Um, I notice I'm not just creating a triangle. I'm creating a triangle out of vectors. No, I'm using tips and tails in a very deliberate way. Notice I'm saying uh, I'm saying the same thing that I ever said with displacement vectors or velocity vectors. I'm saying that to go northeast in Manhattan, to walk northeast is equivalent to walking north plus east, some amount north plus some amount east, right? So, and when you add vectors, you place them tip to tail, right? So I'm very specifically saying that to be pulled down means to be pulled somewhat down left plus somewhat down right. Like, look at the arrows. Like, I'm specifically saying one small component plus another small component equals a hypotenuse. That's the way a right vector triangle should always look in physics. That a leg plus a leg equals a hypotenuse. And notice that the arrowheads are very deliberate. Like, there's many other ways you could have drawn this triangle, but they'd be wrong. Like, like I don't know how to no what I guess I'm trying to say, and then I'll move on, is both of those components that are adding together to make the full hypotenuse, both of them point down-ish. One is down to the left and one is down to the right, but they're both down. Down left plus down right makes down. Not any neither of them could have pointed up in any way, but like a lot of people do that if they don't get used to this. Excuse me. So one of them is mg sine theta, and the other is mg cos theta, and the only question is which. And again, remember, if you've just memorized that sine always is like vertical and cosine is always horizontal, that will get you into trouble here because it's not clear, because neither one of them is vertical or horizontal, right? You don't want to think of sine and cosine that way. People do it first, but you don't ultimately want to think of sine and cosine as like linked to y and x or something like that. They're linked to opposite and adjacent, right? So one of these is okay. And so again, what I'm saying in English is no matter what, planet Earth is pulling down on the marble, pulling straight down toward the center of the Earth. Like that's what gravity is doing. End of story. But now we've put our whole situation on an inclined plane. So the effect, so this is what these components mean in English. The effect of gravity pulling straight down is that to some extent, that sends the ball along the plane. And so literally that means a fraction of the ball's weight is pulling it along the slide. But another fraction of the ball's weight is pulling it into the slide, like against the surface, keeping it on the slide. The weight of the object is doing it's like being distributed to two different jobs. And those two different jobs are what we're calling the force components. The question is, which one is sine and which one is cosine? And by the way, let me also tell you that you don't want to memorize the answer to this because everything I'm saying right now, when I say which one is sine, which one is cosine, I mean which one is sine of theta and which one is cosine of theta. And theta, we presume, is the angle of the whole inclined plane that was given in the first place that you measured in the lab or something like that, right? But anything I'm saying right now totally like depends on that theta. When I'm saying mg sine theta or mg cos theta, I mean the theta that you know in the lab. And let me be clear, I'm just assuming because of the lab instructions that the theta you measured is the one uh, right here, like the theta between the plane and the horizontal and an imaginary and the lab tabletop, right? That's not a law of physics that you had to have measured that angle. Like this entire lab or a final exam question or something like that could be such that it's the top angle that's given or measured. And then every single thing that I'm saying right now would be flipped. And I'm not saying that to trick you or intimidate you. But like what I'm trying to say is the general principle here. There's nothing that don't memorize. Like it's always mg sine theta over here and mg cosine theta over there. No, it totally depends what angle was measured. Okay, so in this case, the angle that was measured, the angle that's known apparently, is the angle that's given from the horizontal axis. That's what we mean by theta. So the question is, when we're dividing gravity up into components, which of the angles in this, I'm going to zoom in again, just so I'm zooming in. If we're trying to figure out, uh, we're trying to figure out which one of these legs is mg sine theta and which one's cosine. Uh, So what I was trying to say Monday is that the real issue is which of the angles in this triangle is the same as the theta that you measured in the lab between the plane and the horizontal. Like that's the way I put the issue Monday. And I answered it, and you may already know, like I answered it. I said it's the top angle that's the same. And that's true. But I want to tell you now a different way of thinking about this. If that lost you, or if you lost that, if that didn't work for you, like yes, I mean I am saying that's the answer. I mean that's the but Oop. Okay. For those of you, this thing I'm about to say now is the new piece of information. Okay. I'm still talking about the topic from Monday, but now I'm giving you a different way of looking at it. And again, this is like a trick, it's a technique that I think is like really important in physics for the rest of our physics lives, which is this. If you're ever deciding it, first of all, if you get to the point in any physics problem ever where your issue is, okay, I've got a diagram here, blah, blah, blah. I've got components. One of these components is blah times sine of theta, and one is cosine theta, but I don't know which is which. Whenever that, I want you to remember this right now. Like in Physics 204 next semester, right? Anytime you have a moment where you're like, oh, I don't know which one is sine and which one is cosine. I want you to remember that I'm telling you right now, welcome to the physics club. If that is your problem in physics, that you don't know which component to make sine and which to make cosine, that means you have done a lot of things correctly to get yourself to that point. Like, honestly, that is a typical classic physics stress. Which do I make sine? Which do I make cosine? If you're even engaging in that stress, you are in the right place at the right time, and you've done all the other work correctly, probably. I'm serious. But now there's a way, and it's important to have that moment be like, oh, I'm having a sine cosine problem. Okay, that means I'm a physicist. Like, okay. Then once you can recognize, oh, I'm having a sine cosine choice. Okay, there's a thing you can do always to resolve that choice. It only works if you know that you're having that choice. But the thing to do always when you're like, oh, which one should be sine and which one should be cosine? The thing to do always is remember that sine of zero is zero. Okay, again, I'm telling you, this was like if I could have had a tattoo when I was an undergraduate, it would have been sine of zero is zero. I mean, that's weird, and I didn't, and that's too much information. But like a key to getting through physics in general is always remembering that sine of zero is zero because now watch this. Or I mean, like, hang with me here for a second. Because that's math, right? Sine of zero is zero, like always. So how that translates to physics is if you're trying to choose which of two components is the sine component, you just ask yourself, okay, physically, if I go to the limiting case, if I go to the extreme case, which I can visualize in my mind without math, if I go to the extreme case in which the angle is zero, in other words, in this case, if I imagine a zero inclined plane, like that the ramp is like flat on the lab table. If I imagine that, which one of these two components should physically disappear? That is an ironclad test from resolving the issue is you test, and this is a trick in physics in general called limiting cases. You go to an extreme case for which you know you can figure out the answer without math, and whatever the answer is in that case whatever the procedure is in that case had better be the procedure for all the harder cases because it's like one law. So I'm saying, look, if the inclined plane were flat, if the angle were zero, like all this logic had better still be true. If the inclined plane were at angle zero, then which of those two jobs would gravity no longer be doing? And in fact, maybe I should ask you. Maybe this is a time I should. Yeah, I think I want to pause. I'm going to repeat the question, then I'm going to ask you in direct chat to either tell me an answer somehow in English or tell me you don't understand the question or whatever. I'm going to wait till I get three responses in direct chat. Here's the question. If gravity, sorry, if the angle of inclination were zero, which job would gravity cease to do? Would gravity cease to roll the ball along the plane? Or would gravity cease to keep the ball on the plane if the angle were zero, if the plane were horizontal? would the weight of the ball no longer send the ball along, or would the weight of the ball no longer pull the ball against the plane? Do you see? So please, in the direct chat, at the very least, okay, someone put it in public. Okay, I'm gonna because he went public. Great. Okay. Oh, cool. All right. Well, okay. I'm gonna yeah, keep going. Keep going. Okay. So someone put a. Sorry, I do appreciate the participation. I love this class. I can't wait to see you guys in 204. I'm not kidding. Keep going. All right, cool. I'm getting a lot of, actually, I did get three answers, which is what I wanted. I mean, two were private, one was public, and cool. Oh, and they were all consistent. Sorry. Yeah, keep going. I don't want. I don't want to cut off the thing that's making me so happy and why I'm laughing is it is so clear from the, I'm not saying right or wrong answers. You should still, if you're with me, you should still put something in the direct chat. Whether you think the other people are right or wrong or whatever, it doesn't matter. First of all, you can get the points. But second of all, screenshot, blah, blah, blah. But second of all, what's making me so happy is such a relief that it's clear, it is clear to me that you do understand the question I'm asking, which I think is really important because often people don't with this question. So, can I repeat the question? Yeah, can I rephrase the question? Okay, yeah. And keep the answers coming in the direct chat when I do. Here's my question. If theta were zero, if the plane were like this, would gravity no longer, which job would, which component would disappear? Which job would gravity no longer do? Would it no longer send the ball along the plane, or would it no longer keep the ball on the plane if the plane were at angle zero? That's my question. So I'll wait, and I have gotten a lot of answers, which is great. I'm just going to wait for like a couple people, the people that asked me to. Awesome, awesome. Okay. And I'm going to wait for the one other person that. Great. Cool. I'm just going to wait. Oh, great. Okay, I've gotten a ton of answers, including the two people that just asked me to rephrase, which I really appreciate, and which you should submit for double points, like the portal that says can you, and I know I'm behind on all the points, but they're there in Google. You know what I mean? Like I'm behind in allocating them back to you, but believe me, they're going in your. You get my point. It just means a lot to me that you guys are participating like this. And yes, I've gotten like 10 answers in direct chat. And honestly, they're all the same correct answer, which is great. The answer is, the answer is, if theta were zero, mg would no longer pull along the plane. It would only pull into the plane. And that's what like all of you said. And if you think that's an easy or at least a clear question, that's great because what I'm trying to say, that does take people a little like this is a trick because not everybody gets it at first. But once you get this trick, it's universal. And what I'm saying is, look at this triangle here. Like this component here is the along component. It's the along the plane component. And this one here is the like into or against the plane. And how do I know that, by the way? Again, not because you would memorize this triangle and say, oh, that triangle always means that. Like, not at all. Like, your plane could be tilted a whole different, you like your triangle. And I want to make this clear too. I know for some of you, this is like, I get it. But for some of you, it's not. Like, for many of you, the triangles that you're drawing in your lab reports are exactly flipped from my triangle. Like everything that I have on the left, you might have on the right because your whole plane might be going like this, and that's totally fine. Right. And this is why we do the 5-step method, like step one, DFP, and then we do other things. Because what I need to make clear to you right away where to keep going. Yeah. Like in my head, in my lab that I did, my plane looks like this yellow picture up at the top or the yellow picture down at the bottom, right? I have to tell you that so you can picture what I'm picturing. Yours might be the opposite. It might be going the other way. Totally fine. But you got to make that clear to yourself and everybody else, right? But if assuming that my plane looks like that, then my free body diagram looks the way it does, right? And gravity's pulling straight down. So then when I divide gravity up into components, when I zoom in on gravity, there are my two components. One is along the plane, right? In the way that I've drawn it, and the other one is against the plane hopefully you see that. Again, this is not about memorizing. It's about like seeing the connection among the pictures, the connections among the pictures. So now what I'm telling everybody, and again, of course, I know some of you already understand this. I mean, okay, to help your friends then, I'm saying then if the along the plane arrow is the one that has to disappear when theta is zero, then that means that the along the plane arrow has to be the sine component and the other one has to be cosine. That's the take. I'm going to move on. I know I'm yelling. I'm yelling. Uh, 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 but really, again, I mean, I'm like literally like it's like it may not be to the extent that physics is group therapy for the math traumatized or whatever. Like I'm literally working out to you. I mean, well, I'm 54. I was 22. I'm working out for you like trauma that I had 30 years ago. Not understand. I remember not understanding the whole sine cosine thing and I remember like being even thrown like, why the hell, if gravity is just straight down, why are we dividing that into sine and cosine? Like, and I couldn't get the sines and cosines straight. Now, I think a lot of you are smarter than I was. I'm seriously like, I think for a lot of you, it's coming a lot quicker than it did to me 30 years ago. On the other hand, I think there are some of you that think it's coming quickly to you because you're just like, yeah. Can we move on? Let me, and no, the way to really get this is to first engage in what there is not to get and then unravel that and get to what there is to get. What I'm saying is it turns out to be a huge trick in physics to always understand sine of zero is zero. So whatever component disappears in the theta zero case will be the component that is sine. Always. If you get that I just said that, that is universally reliable and it gets you out of the sine cosine jam every time without having to do complicated geometry. So I'm saying here, oh my God. Wait, someone just said, yeah. I was just gonna thank you, direct chat person, for the yay. I'm not even sure what the yay is for, but like, good. If one person feels slightly better, then I feel much better. Okay, so what does this all mean then? And the other reason I'm dwelling on, I know it's already 11:30, but I think this is the hardest part of well, anyway. All right, so now, but certainly the part that has applications to a lot of other physics. All right, so that therefore, the up trip component FBD looks, well, so therefore, I've now decided, I'm going to flip back again. I've now decided that MG is really the sum of mg sine theta plus mg cos theta, right? That's what I've decided by this zoom in situation. Therefore, therefore, from now on in my diagrams, I don't put mg at all anymore. Instead, I put mg sine theta and mg cosine theta. And boy, talk about a pro tip. I'm telling you right now, you know how I'm behind your exams? Yes, I'm behind on your exams. Well, I'm also doing a bunch of 204 exams right now. And they have a free body diagram in their exam. Like, obviously, it's different material and all of that. But there's a free body diagram in one of their problems in 204 right now, where every single one, no, I shouldn't say that at all, where a lot of them have mg sine theta and mg cosine theta in a complicated thing that's whatever. And then they also have MG in the diagram. I'm telling you, right, it's driving me crazy. In fact, I'm going to blame them for the fact that I don't have your exams finished. They're slowing me down so much. No. But I don't know what's gotten into me today. But like, why is today any different from any other? But what I'm getting at now is you go through this work of dividing up a force into its components so that you can ditch the force itself and replace it with the components in a component diagram. Don't put both. If we're now going to make a component diagram, mg is not going to be in it. If mg is in it along with mg sine and mg cosine, you're literally double counting gravity. You're saying gravity is doing three. Like, don't do that. The point and what the point is to only now have forces that are directed along coordinate axes, x and y. So my component diagram now is n going like that, and this is the up friction going like that, mg sine going like that, an MG cosine going like that. Yes? And please stop me. And I know you know this, but just stop me if that. But I think that is the diagram for something on its way up, assuming my plane is oriented that way, right? That's the up trip. I'm going to keep going with the up trip, right? So now who cares? What's the point of this? Now, and this is always the procedure for all Newton's law problems, now that we have a free body diagram that only has vectors in it that are only pointing along axes, now we can apply Newton's second law. That was the point of doing all of this. The sum of all the forces along each independent axis yields, causes, equals the acceleration divided by mass times mass uh, um, of the object along each independent axis. In other words, we're now going to apply the vector equation F net equals ma, which really means, and this is the point of why we just did all this work, what that really means is that the sum of all the x forces produces the x acceleration, while simultaneously yet independently, the sum of all the y forces produces the y acceleration, right? And this is what we're now going to, like, we did all these pictures so that we can now do this math. But this math demands that we expand the left side. Like the left side says sum of all the I mean SUM of all of the forces produces the acceleration. So the whole issue is what are all the forces on each axis one at a time? Well, now we finally know because we have a picture. Okay, so we'll so we're going to do F net equals MA independently on each axis. And here's the pro tip again from Monday. Excuse me. And this is where like it really begins to matter. I really have simultaneous equations. I have a equation, Newton's law along one axis and independently but simultaneously along the other axis. Pro tip is I always start with the axis that I don't ultimately care about. What do I mean care about? Like, I mean that the ultimate issue of this whole lab is all you're what we're ultimately examining is the trip up the plane versus the trip down the plane. We're ultimately trying to learn something about the acceleration up the plane versus the acceleration down the plane, meaning along the plane itself. The x-axis. We've lined right the x-axis because we've called that the x-axis. So I always start my analysis with the other axis. I leave the punchline axis for last. So we go okay, so right, I'm okay. So this is right. So this is Newton's second law applied to the y-axis. I look at the y-axis. I look at all the I look at my picture. I add up all the forces in the y-axis. I see N and I see mg cosine, right? But they're going in opposite directions. N is going in what I've called the positive direction. Where to go? Right? N is going in the positive direction, and mg cosine is going in the opposite. So it gets a negative sign, right? Again, I'm looking at the time. Again, I just want to remind you that looks like subtraction. I mean, it is subtraction, but what's the logic? This thing right here means add up all the forces in a given axis. So you're always adding. It's just that some of them might be getting minus signs going in opposite. Okay, I think you get my point, but stop me if you don't. So I say this, hello, right? Okay, and this is what I warned you about Monday. Maybe I guess I've already done this. Okay. Why am I doing this? I'm doing this because I'm going to get information from this axis that I'm going to use in the other axis. What information? The information of the normal force. I'm really looking at the y-axis first because the normal force is acting on the y-axis. What I know is that along the y-axis, the acceleration is zero. Now, this is a subtle point too. I'm trying to watch the time. I'm trying not to get all. And again, you should. uh, I know, like it wasn't. You're not like told in the lab or something like that. But I know that the acceleration along the y-axis is zero because of the way I chose my axes. And in fact, this is one of the reasons that we choose our axes this way. Again, this is Galileo's principle. Is you could choose the axes anyway, and the laws of physics had better still be the same. It's a very deep observation. Um, and so we'll get to, so you could make other choices. And if you're really careful, the physics should still work out and all that. But we strategically okay, so to be really clear, when I say the acceleration in the y-axis is zero, I don't mean that the ball has no component of downward acceleration. I don't mean that. Like, obviously, the ball is like rolling along a slant, like it is accelerating somewhat down-ish. So if by y you're thinking in your mind down, well, then you would be confused by like, where did I get this statement from? But y-axis doesn't mean down. We've tilted our axes, right? Y means a perpendicular to the plane. And we deliberately tilted our axis so that all of the x-axis lined entirely up with the direction of acceleration. Or put another way, we deliberately set things up in our mind so that the acceleration of this ball is entirely what we're calling x. Therefore, there's no acceleration along the y. It couldn't have been given as in the lab. No one could have told you this because it's totally dependent on the choice that you're making for analysis. But in that choice, the acceleration along the y-axis is zero. Therefore, in, and this is one of the reasons that this is a good choice. It simplifies the calculations enormously. Therefore, n minus mg cosine theta equals zero. So therefore, n equals mg cosine theta. This is a way of saying the ramp is supporting a portion of the marbles. Right? Do you see what I'm saying? And again, this is if you're with me, which I think you are, it's not a memorizer. It's not a formula. N equals mg cosine theta. No, in many other situations, n doesn't equal mg cosine theta at all. And sometimes it has nothing to do with mg at all, et cetera, et cetera. But here, in the case of an inclined plane, n is equal to mg cosine theta. Remember, cosine theta is always a fraction. Oh, my internet connection's unstable. Okay, well, so is my psychology. The n is mg cosine theta is a cosine theta is a fraction. So mg cosine theta is a fraction of mg. You know what I'm saying? It's like mg times. Oh, am I glitching? Yeah. Sorry if I'm glitching. My computer just also said that I was glitching, but I don't know what to do about that. Hold on one second. Sorry. Um. Huh. Okay. No, it's not you. So a number of people are telling me I'm glitching. It's not you because my computer just said that too. But I don't know what. Is there a trick to? Oh, I'm fine now. Oh, I'm fine. Thank you. So I'm fine now. All right. Keep. Thank you guys for. And by the way, again, that just totally shows how much it's good. Okay, boy, you guys really are paying attention. So, all right, so let me pause for a second. I mean, because we have 20 minutes, right? If I is this should I like speed this up? Or is this all? Or, no, of course we're paying attention. Fair enough. No, yes, you are wonderful people. I don't know. Yes. But wait, okay, so since you're paying such attention, I mean, obviously should I be speeding this up, or are there any questions about what I'm saying so far, or also, or is it like all obvious? Should I just get to the, well, you privately tell me like if you want this faster or slower, or like, or if there's something specifically you've been waiting to hear, I can get to that. We still have 20 minutes. I mean, well, okay. Okay. All right. Of course we're paying attention. Okay. So what I'm trying to say is this just showed in the case of this inclined plane, what the ramp is doing is supporting a portion of the weight. It's not supporting the full weight of the ball. N does not equal mg. It's supporting a portion of the weight. That's why the ball is still falling. It's only, okay? So N equals mg cosine theta. So I just leave that. That's a fact about the left. I just leave that. Now I go to the other axis, the one I care about, right? And I look at the X, I look at the picture. It's all about the picture now. The picture says in the X axis, I have two forces. They're both pointing in the same direction. That direction is down. I'm calling that direction positive, which I highly recommend for the lab. In fact, okay, it's 11:45. Real pro tip for the lab, call the down direction positive in both cases, whether the thing is moving up or moving down. Now, this is a strategy. You don't have to do this, but it's going to be a lot more confusing if you don't. Um, and you're going to get things like there's a lot more room for error if you don't. I'm saying the ball is accelerating this way, so make this way positive in both cases. Therefore, in this is I'm talking about while the ball is traveling up, right? It seems to me, according to my picture, and I'm just literally copying from the picture, mg sine theta plus friction equals max, right? I guess I did do that. I guess I am sort of dragging this. I guess I did do this Monday, but I apologize. Um, and friction, friction always equals mu times the normal. We explained that the week before break. I said Monday again. Stop me if you don't understand that. That if anything's a memorizer, okay, that's a memorizer. Like I think it makes sense. I hope you understand why it makes sense. But it's true that it's just true. So I substitute in. I mean, what that means, as I keep trying to say, is it means that friction like this is the result of rough surfaces going like that. The more the rough surfaces push down against each other, the more they microscopically lock, like teeth of a comb, and the harder they are to go like this. That's what that statement means. So we have this, right? Um, and the normal force is what I wouldn't have known but for the y-axis, right? So I substituted in. Right? And then I could divide both sides by m. I mean, I could factor out an m and divide only because there's an m in every single term, and I could factor it out. Therefore, I could divide both sides by m. So now I can say, now this isn't like a answer, but it's a pretty important piece of information. Okay, we have 18 minutes left, 17 minutes left. Okay, let's pause for a second. I mean, I could analyze this thing all day. But what this is saying, oh, in fact, wait, I don't want to analyze it all day, but do I want to say, okay, Like, like this is the acceleration that the ball is experiencing while it's on its way up. Now, this acceleration is pointing down, right? Just like when you throw something up, it's accelerating down, meaning that when it would be traveling up, it'd be losing speed, right? Consider, I'm saying that the acceleration on the way up is the sum of these two pieces. For a moment, for a quick moment, consider each piece independently. Look at the first piece, g sine theta. What is that? That's just the effect of gravity on the ball, the effect of the weight of the ball, of its own weight on the ball. So remember, sine of zero is zero. Always remember, sine of zero is zero. And from that, I say sine super, cosine crappy, or cosine counterintuitive, sine super. What I mean is the sine of zero is zero, and then as the angle gets bigger, the sine gets bigger. Always, always, right? Sine is like what you'd invent if you had to invent these things on a desert island. Cosine is crazy. Cosine is counterintuitive, it's the opposite. Cosine of zero is one. And then as the angle gets bigger and bigger, cosine gets smaller. I'm not saying that that doesn't make sense ultimately. Ultimately, it totally makes sense. But it is the one that's confused or cosine confusing, let's say. Sine is your friend. It's the one that makes the most immediate sense. And why I'm bringing that up is look at, and remember, sines and cosines are always like fractions, decimals, percentages in effect. So what that first term is saying is that the greater you make the angle of inclination, the greater you tilt this plane, the greater percentage of free fall acceleration this ball would experience if there was nothing else going on. Like if there's no friction at all, if the angle is zero, the ball wouldn't accelerate, wouldn't free fall at all, right? It would be zero times g. As you make the angle bigger and bigger, if the angle is like 30 degrees, then the ball would accelerate down at sine of 30 times g. In other words, a half of g. If you make the angle like 30 degrees, the ball will accelerate down at 4.9 meters per second squared rather than 9.8, right? And if you bring up the angle to 45 degrees, then it'll be like radical 2 over 2 times G, i.e., like 0.707, 71% of G. Then you bring it up to 60 degrees, it's like 86% of G. And then you bring it all the way to theta equals 90 degrees. The sine of 90 is 1. It will be 100% of G. Doesn't it make sense? It totally may. I mean, I think it totally may once you think about it. So the first term is just saying the greater the angle, the greater percentage of free fall we'll experience on our way down if there's no friction at all. But then there's friction. So now friction is adding even more, adding. Now it seems odd. I'll get to that in a minute, but it's adding more negative acceleration, right? And how much? Well, now this is dependent on the cosine. The cosine works the opposite way. So the flatter it is, there's a lot of friction because the flatter it is, the more the ball is being pulled into the plane, right? So they're squeezed together more. So you get a bigger and bigger percentage of free fall acceleration being like yeah, you get a bigger percentage because you have more friction the flatter the plane is. You see what I'm saying? But they're adding together. Now we have 12 minutes. They're adding together when the ball is on its way up. This is where it starts getting, this is like a little bit surprising, maybe, or you have to think. I'm saying, well, here, hold on. I'm saying on the way up, and this is what you want to talk about. You want to think about and then talk about in your way in the lab while ball is on way up. Both forces working together I'm saying both the forces, when the ball is on its way up, all the forces are working against the ball. Like that is true. That is why, like intuitively, people would think, well, it's harder to go up than to come down. I mean, I'm not saying that's not true in a way. All the forces are working against the ball, yes, but they're working together. Mg sine theta and friction are both working together to produce a very large magnitude of net force while the ball is on its way up. A large magnitude of net force while the ball is on its way up, and therefore a large magnitude of acceleration. The thing that's confusing, perhaps, or the thing you have to straighten through, is that this acceleration is negative. Okay, the acceleration is in the opposite direction from the velocity. That is true. So what does that mean? It means it represents slowdown. I mean, it represents a loss of speed, right? It's negative acceleration. So it's a loss of speed, but it's an enormous magnitude of loss of speed. Say, look, just to, okay. As an example, just to simplify things, imagine that the mg sine theta term is is three, or sorry, that the g sine theta term is three, and imagine that the mu g cosine theta term just is like two in magnitudes. Okay, well, they're adding together. So you have a magnitude of five. So the ball is on its way up, has an acceleration of five, but it's negative five. So what that meters per second squared. So what that means is every second, this ball is losing 5 meters per, 5 meters per second of speed every second, right? That's what's happening on its way up. Now, compared to the down trip, we have 9 minutes, right? Compared to the down trip. Of course, I'm not going to like repeat the whole, I'm just going to get to the punchline. If you go to the down trip, the component free body diagram looks like this. We got sorry, we've got mg sine theta still pointing down. We've got mg cosine theta pointing down against the plane. We got normal going up like this. But now on the way down, we've got friction pointing up, right? I'm not saying they're equal and opposite. I'm just saying they're opposite. So now to cut to the chase, in the x-axis, we have mg sine. So in the x-axis, F net equals ma. We've got mg sine theta minus mu mg cosine theta equals max, right? If we're on our way back down now, right? And so the m's cancel. So on the way in this direction now, we have ax equals g sine theta minus mu g cosine theta. So now they're in conflict. Granted, what's confusing is now it seems like you're on the way down, like it seems like gravity is helping you. And I'm not saying that isn't true. What's true about that is now you're on your way down. The acceleration is still pointing down, but now so is the velocity. So now you are speeding up. Yes, you are speeding up now. But look, the friction is in conflict with the gravity now. So now magnitude of F net and of A is smaller. The magnitude is smaller. So if, for example, in our example, we just made up, like, just to cut to the chase, we made up that like g sine theta was 3 and mu g cosine theta was 2, right? Then now A would equal 3 minus 2, 1, as opposed to 5. What I'm trying to say, I'm watching, we have 6 minutes. What I'm trying to say, on the when the ball's traveling on the way up, if you just take these example numbers of 3 and 2, the numbers don't change. It's just a question of whether they're being added together or subtracted from each other. Like that's what I'm trying to show because of the diagrams. So like when the ball is going on its way up, it's accelerating at a rate of, let's say, 5. That means it's losing speed at a rate of 5 meters per second every second. Then on the way back down, say its acceleration is 1, it's gaining speed at a rate of 1 meter per second every second. What I what I'm saying is the ball loses speed at a rate that's quicker on the way up than it gains speed on the way back down. So what that means is like because the ball starts with some initial velocity, say 25 meters per second, whatever, some initial velocity, and it does, and it literally doesn't matter what it is. Then the ball is going to go up. The ball is not trying to get to a particular location. You never said the ball has to get here and then I'm going to send it back down again. The ball just goes up until it runs out of speed, right? So it starts with some initial velocity like 25. It's oh, good. I'm glad. Thank you, direct chat person. Good. I'm hoping. Okay, good. And maybe this will also help. No, I totally appreciate that feedback. Um, so I'm saying, like, on the way, like, because everybody, let me back up for 1 second. I'm watching there's 4 minutes left. Like, everybody thinks that somehow, like, the initial flick, the initial velocity is what makes all the difference. People tend to end up thinking, oh, I guess it's faster on the way up or something because, like, I flicked it on the way up, but I didn't flick it on the way down. No, 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 no. That is not, yes, you had to flick it in order to get this thing going, but that's not making the difference at all. Here's what I mean. You flick it, you give it like an initial velocity of 25 or something. So now it's rolling up. And what is its job? Its job is to run out of speed. Like it's going to start coming back down or it's going to stop going up once it stops going up. So if it started with 25 meters per second of speed, it's losing 5 in this example every second. So like, shoot, it like, in 5 seconds, it's done with its speed. So now it's got 0. Now it starts coming back down. It's got to head back all the way back to where it started from, right? It's coming back down, but it's gaining back its speed at a dribbling rate now. It's gaining back its speed at a slower rate. So by the time it gets to the bottom from which it began, it hasn't had sufficient time to gain back all of its original speed. So no matter what its original speed was, say it was 25, it goes like 25 to 0 and then 0 to 17 or something. So on average, on the way up, it's the average of 25 and 0, like 12 and a half. On the way down, it's the average of 0 and like 17. 9, 8.5. Really, this is right. I'm saying, on the one hand, if you don't understand physics or you don't follow this, you're like, on the way up, it's like slowing down, and on the way down, it's speeding up. So obviously, it's easier to come down. Well, that statement is true, but the inference is not true. Even though it is slowing down on the way up and speeding up on the way down, it's not doing that at the same rate. It is slowing down more quickly on the way up than it is speeding up on the way down. And so on the way down, it doesn't have time or space to gain back all of what it started. Right? That's what I'm saying. I mean, we have 2 minutes, right? I'm just saying it loses speed on the way up at a greater rate of acceleration than it gains speed on the way down. And that is entirely because friction flips to help gravity on the way up, whereas friction is opposing gravity on the way down. I should say it's entirely because friction flips and gravity does not. Like that's the asymmetry in this problem. So the net force is enormous while the thing is going up. and the net force is small when the thing is on its way down. Yes, the direction is against velocity. The direction is what you think, but the magnitude comparison is what makes the difference in the whole thing. Hopefully that's clarifying. I mean, obviously you still have to do numbers and all this other kind of stuff in lab, but that's like the concept. And you'll know you get it if once you it's 1205. You'll know you get it if once you look at your diagram, it's like, oh yeah, it's just in the arrow. Okay, it's all about that arrow. Yes, it's all about that arrow. Okay. I will keep catching up. You're very patient. You're very kind. Oh yes. Oh, good, good, good. Oh, cool, cool, cool. Okay, thank you for the feedback in the direct chat. Awesome. I'm turning off the recording. Yes, bye. Thank you. Yes. Okay. Um, okay, bye.